We'll now continue on with part 2 of our Math 110 final exam review, picking up with question number 26. In question number 26, we're asked to find the inverse function for f of x equals 3x plus 5. If we recall from earlier, there's a bunch of steps we want to follow in order to do this. The first step is to revert back from f equals to the y equals notation. So instead of calling it f of x, we're going to call it y. The next step is we're going to do the interchange, where we're going to replace the x and y variables. In the equation, everywhere you see a y, put an x, and everywhere you see an x, put a y like this. The goal now is to take this rewritten equation and to get the y by itself. We can subtract 5 from both sides. That produces x minus 5 equals to 3y. We can now divide both sides by 3, and what we come up with is y equals x minus 5 divided by 3. This new expression for the variable y isn't the same as the original y expression we started out with. This is actually our inverse function. So we can now return back to the inverse notation. Everywhere we see a y, we're going to put f inverse of x, which is x minus 5 divided by 3. So that's the key to finding an inverse function. It's 3 steps. You revert back to the old school notation. Instead of f of x, call it y. We then interchange the x and the y variable. You then take that new expression, solve it for the y variable, and once you have y by itself, that function of x is actually the inverse function f inverse. One of the things that I've always asked us to do, and this will be the same, is whenever you come up with an inverse function, we want to verify this. So the key relationship between a function and its inverse is that when you compose them, it should be equal to x. So let's do f composed with f inverse of x and show that this equals to x. So the outer function here is f, so starting with f, which is 3x plus 5, or another way to say it, it's 3 times my input plus 5. I'm going to plug into that the function f inverse, which is x minus 5 over 3. Nice and neatly, we want to highlight the steps that are worked here. The multiplication by 3 and the division by 3 cancel. That leaves us with x minus 5 plus 5. The minus 5 and the positive 5 cancel, and so that does produce the value x. We're not done verifying it, though. We have to show the composition in the other direction. Let's now look at f inverse of f of x, and let's show that that too does equal to x. So now we're going to start with f inverse. F inverse as a function says take your input, subtract 5, and divide it by 3. My input is the function f, which is 3x plus 5. To simplify this, notice that the positive 5 and the negative 5 cancel. So we get 3x divided by 3. The 3's cancel, and so that 2 gives us x. By showing both of these compositions equal to x, this proves that x minus 5 divided by 3 is indeed the correct inverse function. The next thing we come to is the graphs of our polynomials, and we started off with graphing quadratic functions. In question 27, this is a quadratic function that's presented in standard form. It's of the form a times x minus h squared plus k. We can look at it and identify the vertex is going to be located at 4, 2. It's a polynomial, so we know that the domain is going to be all real numbers. Next thing we want to do is discuss the range, and this is where we need to consider the value a. Because a is equal to negative 3, that means that this is going to be one of those parabola that opens down. And because it opens down, that means that the vertex is going to be a maximum. Okay? We would say, and I'm going to rewrite it compared to how they want you to put the answer here, but remember, the maximum value is the y-coordinate. So it has a maximum, I'm going to say, of 2, And then where it occurs at, it's at this x coordinate, at x equals to 4. Okay, so be very careful. This is important that you understand this. When we're talking about maxes and mins of functions, the max and min is the function value itself, which in ordered pair format would be the y coordinate. The location of that said max or minimum is the x value of that coordinate. So we would say that this particular function f of x, it has a maximum value of 2, and this occurs at x equals to 4. Knowing that, this will also help us to find the range. We know that this is a parabola that opens down, so on the y-axis it's going to go all the way down towards negative infinity, and because it has a maximum of 2, it's going to go as high as the value of 2, which would be included. Okay. So that would be our range for this function, and we can also go ahead and give a very detailed sketch of this thing. So if we wanted to graph negative 3 parentheses x minus 4 squared plus 2, so this is equal to f of x. We said we knew a few things. We said we knew that the vertex was at 4, 2, so that's 1, 2, 3, 4, up at 1, 2. So here's our vertex. We also know that it's going to open downwards. To give a more detailed graph, it wasn't asked for in this question, but we'll see it in the next question. You would also want to know the x-intercepts. So you should set the function equal to 0. And I'm just going to skip that part because it's not part of this one. It's actually going to be a little bit sloppy. But you're going to get a graph that ultimately kind of looks like this. This is a very, very rough sketch of negative 3 times x minus 4 squared plus 2 equals to f of x. In question 28, we now have the function f of x equals x squared minus 2x minus 3, which is yet another quadratic equation. And in the first part, they also ask us to find the vertex. Okay. This quadratic is not presented in vertex form. It's actually presented in like general form. When you have a parabola or a quadratic that's presented in general form like this, you need to use the vertex formula. Okay. Very important formula. We also use it for quadratic applications. Please make sure you know this. The x-coordinate of the vertex is at negative b over 2a, and the y-coordinate of the vertex is going to be at negative f of negative b over 2a. Here, in standard form, we see that a is 1, b is negative 2, and c is negative 3. It's hard for me to write my c when this thing's getting in the way. But c is going to be negative 3. So let's find the x-coordinate of the vertex first. It's going to be the opposite of b divided by 2 times a. That's going to be the opposite of negative 2 divided by 2 times 1, which is going to be positive 2 over 2, which is positive 1. So 1 is going to be the x-coordinate of the vertex. To find the y-coordinate of the vertex, we simply plug 1 into the function. F of 1 is 1 squared minus 2 times 1 minus 3, which is 1 minus 2 minus 3, which should be equal to negative 4. So vertex formula, extremely useful. We find that the vertex is going to be at 1 comma negative 4. I'm going to skip over to another part where they actually ask for the axis of symmetry. Remember, the axis of symmetry is always, for this, x equals the x-coordinate of the vertex. So your axis of symmetry is going to be x equals to 1. To find the x-intercept, you set the function equal to 0 and solve. So x squared minus 2x minus 3 equals to 0. This factors as x minus 3 times x plus 1 equals to 0. Set each factor equal to 0 individually, and we get x equals to 3 and x equals to negative 1. These x-intercepts are points, so let's write them in point format. That's 3, 0, and then -1, 0. So those are our x-intercepts. The y-intercept is a function evaluation. You just evaluate f at 0. This is going to be 0 squared minus 2 times 0 minus 3, which is -3. Again, the y-intercept is a point, so write it as a point. We get 0, -3. And then once again, they ask us about the max or min value. So let's kind of go ahead and let's take a look at what we have here. So we've already found our vertex, which we know in a parabola is going to be the location of that max and min value. But to determine what we have, we need to look at the leading coefficient. The leading coefficient here is a, which is 1, which is greater than 0, which means that this parabola is going to open up. And anytime a parabola opens up, that means that the vertex is going to be a minimum value. So we would say that this parabola, or this quadratic function, is going to have a minimum. The minimum is -4, and this occurs at x equals 2 to 1. So we have a minimum of -4 that occurs at x equals 2 to 1. And then the last thing we're going to be asked to do is to give a sketch of this. We have our important points, namely the vertex, the intercepts. We know the axis of symmetry, and we know how the graph opens up. So we should be able to give a very good detailed sketch of this graph. Here's my y-axis, here's the x-axis. Vertex is at 1, -4, like this. We have a x-intercept at -1, 0, and at 3, 0. Here is our vertex. We also know that the vertical line through the vertex, that equation x equals to 1, is a line of symmetry for this graph, and it opens up, so that should enable us to draw a nice and detailed parabola for this. So this would be the graph of f of x equals x squared minus 2x minus 3. In the next set of questions, we move on now to graphing higher order polynomials. In number 29, we actually have a polynomial here that's in factored form. That makes it easy to find the intercepts. So to find the x-intercepts, you just set each factor equal to 0. So we have -3 equals to 0, x plus 3 equals to 0. We get x equals to 0, and we get x equals to -3. So we have two intercepts. They are 0, 0, and also -3, 0. For the y-intercept, you just plug 0 into the function. If you plug 0 in, you're going to get 0 out. So the y-intercept is going to be 0, 0. And now the last thing they want to know is, what about the degree and the leading coefficient on this? Well, to find the degree, when it's in a form like this, we need to find the leading term. And I described a way to do this in the notes. What you do is you look at each factor, and you take the highest power of x that's located with each factor. So if I look inside of this square parenthesis, the highest power of x would be the x of the first term. So that's going to be what contributes to the leading term, is going to be the x squared term out of that. And if we multiply this all the way out, we get -3x to the third. So the degree of this polynomial is going to be of degree 3, which we know now would talk about the end behavior. So the end behavior of this polynomial is going to be, let's talk about the leading coefficient first. The leading coefficient would be this value here, and we call that a sub n. That's equal to -3, which is less than 0. And by knowing those two together, that will tell us about the end behavior of the polynomial. With an odd leading degree and a negative coefficient, this polynomial is going to go up to the left and down to the right. Let's go ahead and provide a rough sketch of this thing. So we want to graph f of x equals negative 3x times x plus 3 squared. We have a couple key points. So we know we have an x and y intercept of 0, 0. And we have an x-intercept of negative 3, 0. Which is right here. We also know that the polynomial is going to open up to the left and down to the right. One of the things that we didn't do earlier is to talk about the multiplicity of these zeros. And that's an important thing to know because remember, that talks about what happens to the graph near the x-axis. The intercept, x equal to 0, had multiplicity 1. And that means the behavior at the x-axis means that it's going to cross the x-axis at 0. Our x-intercept negative 3 came from a factor that had multiplicity 2. And if you have multiplicity 2, that's when it touches and turns at the intercept. So by knowing that information, I know that the graph is going to do this. It has to go up to the left. So I'm going to have it going up to the left. I need to come down, and I need to hit the x-intercept at negative 3. At x equals to negative 3, because of the even multiplicity, what that graph is going to do is it's going to touch and it's going to turn around. So it does not cross the x-axis. From there, it's going to have to turn around eventually to get back to the next intercept, which is x equals to 0. And notice that x equals to 0 has an odd multiplicity, so it's going to cross, which makes sense because we know the end behavior of this thing is it has to go towards negative infinity as x approaches positive infinity from our leading term test. And so putting that all together, this gives us the graph of negative 3x times x plus 3 quantity squared. Let's take a look at the next one. Number 30 is very similar. In question 30, we are asked to graph f of x equals x plus 2 squared times x minus 1 times x plus 1. Let's start by finding the x-intercepts. You set each of these factors equal to 0. I'm going to do this very briefly. But setting the first one equal to 0 will give you x equals to negative 2. Setting this one equal to 0 will provide x equals to 1. And setting this one equal to 0 will give us x equals to negative 1. I'm also going to write out the multiplicity and the behavior at the x-axis. X equals to negative 2 came from a factor that appeared twice, so it has multiplicity 2. Because it's even, I know it's going to touch and turn at the x-axis. The x-intercept 1 came from a factor that appeared once, so it has a multiplicity of 1, which is odd, and that means it's going to cross the x-axis there. And x equals to negative 1 came from this factor, which also had multiplicity 1, which means it's going to cross the x-axis. Let's see if we can now determine the leading term. The leading term is going to come from each of these factors by taking the highest power of x within each factor. So if I kind of imagine just crossing some of the stuff out, the main contributions to the leading term are going to be the x squared times the x to the first times another x to the first, which is going to be x to the fourth. That is a term that has an even power and a leading coefficient, which is 1, which is greater than 0. If you have an even power and a positive leading coefficient, that means that the end behavior is going to be up and up, meaning it's going to rise to the left, and it's also going to rise to the right. We also should find our y-intercepts. So if I evaluate f of 0, be careful here. This is going to be 0 plus 2 squared times 0 minus 1 times 0 plus 1, which is going to be 4 times negative 1 times 1, which gives us negative 4. So the y-intercept is going to be located at 0, comma, negative 4. And let's put it all together. So let's plot our points first. So negative 4, 0, comma, negative 4 is right here. I have x-intercept at negative 2. We have an x-intercept at negative 1. And we have an x-intercept at positive 1. We know the end behavior is up and up, so I know it has to go up over here. I eventually have to come on down and hit this x-intercept at negative 2. At negative 2, the multiplicity is even, so it's going to touch and turn. So I'm not going to cross right away, but I have to double back pretty quickly in order to hit the intercept at x equals to negative 1. And at x equals to negative 1, notice that it's going to cross, which is good because we have to come down here and pick up that y-intercept at 0, negative 4. We'll eventually have to turn around, and we have to get to the point x equals to 1, which also has an odd multiplicity, so it's going to cross there as well. And that agrees with the fact that we know that the end behavior has to go up to the right. And so putting it all together gives us a very detailed graph of the polynomial function f of x. Let's take a look at the next example. In question 31, now we're moving on to our rational function material. To find a vertical asymptote for a function, you set the denominator equal to 0. This would come out to be x minus 5 equals to 0, which would give us the value x equals to 5. As long as that value, which made the denominator 0, does not also simultaneously make the numerator equal to 0, then that will be a vertical asymptote for your rational function. To find the horizontal asymptote, that's when you compare the highest powers in the numerator and denominator. If you needed to, you could have expanded that denominator to write it like this. X minus 5 times x minus 5 would give you x squared minus 10x plus 25. And then because the highest power of x is in the denominator, that's always the case where the horizontal asymptote has equation y equals to 0. So again, to find the vertical asymptote, you're looking for the values that make the denominator equal to 0. And as long as those don't make the numerator also equal to 0, they will in fact be vertical asymptotes. To find the horizontal asymptotes, it's a matter of comparing the highest power of x within your fraction. If the highest power of x is in the denominator, the intercept is always y equals to 0 for the horizontal asymptote. If the highest power is shared between top and bottom, then it's the ratio of the leading coefficients. And if the highest power of x would happen to be in the numerator of your fraction, then in that case we would say that there is no horizontal asymptote. Let's take a look at number 32. We actually want to graph this thing, but first let's kind of find these key points. To find the vertical asymptote, we set the bottom equal to 0 and solve. We should get x equals to negative 2. So the vertical asymptote is x equals to negative 2. And notice, I can just visually check this. That value of x will not make that numerator also equal to 0. So it is a true vertical asymptote. To find the horizontal asymptote, we compare the highest power of x. Notice that both numerator and denominator share the same highest power of x. So the equation of the horizontal asymptote is going to be y equals the ratio of their leading coefficients, which is 1 over 1, which is just 1. So the horizontal asymptote is going to be y equals to 1. To find the y-intercept, we've done that a bunch of times, but that's a function evaluation. You plug 0 into the function. F of 0 is going to be 0 minus 4 over 0 plus 2, which should be negative 2. So that's 0 comma negative 2. And then to find the x-intercept, that is where you're going to set the function equal to 0 and solve. So for our x-intercept, you set f of x equals to 0. When you're dealing with a fraction, that's equivalent to wherever the numerator is equal to 0. And x minus 4 equals to 0 precisely when x equals to 4. So we get the x-intercept 4, 0. Let's go ahead and put this all together to graph this function. So we had the equation f of x equals x minus 4 over x plus 2. First thing I'm going to go ahead and do is let me plot my asymptotes to begin with. So we said that we had a vertical asymptote at -2 for x. So that's x equals to -2. We also said we had a horizontal asymptote at y equals to 1, like this. So that's the horizontal line y equals to 1. We had some points on this graph. I'm going to put this graph in green. We had a y-intercept of 0, -2. And we had an x-intercept of 4, 0. We now can graph our rational function. We know it has to follow the asymptotes. So over here to the right, we know that it has to look like this. So we're going to have this piece right here. Now, for the second half, if you look at what's going to happen to the left of that vertical asymptote, it's either going to follow the asymptotes above like this, or it has to follow the asymptotes down like that. And without plotting any extra points, although you could, we know that it has to look like this. And the reason why it has to fit this pattern is, notice that if you tried to plot the graph down here, the only way that can happen and follow the asymptotes is it would require the graph to cross the x-axis, which would produce an x-intercept. However, we've already solved and calculated all of the x-intercepts, and there weren't any other ones over here. So that would rule out that possibility, meaning it would have to be above like this. If you don't like that, or if you feel uncomfortable doing that, one of the things that we discussed in the notes is you can always pick another value of x that's over here to the left. For example, if I pick -3 for x, and I plug it into my function, f of -3 would be -3 minus 4 over -3 plus 2, which if you work it all the way out, it's going to be equal to +7. So that point, -3, +7, would give you a point that's up here, and then that would allow you to complete knowing where the rest of the rational function is located at. The next question we come to is now our quadratic inequalities. Let's take a look at one of these. This is 33. So it's the quadratic inequality x squared minus x is greater than 6. The first step to solving a quadratic inequality is to get one side to 0. So let's subtract 6 from both sides. I'm going to call this x squared minus x minus 6 is greater than 0. And then we're going to define, let's call the left-hand side, let's call that equal to f of x. We are now going to use f of x to find the boundary points. If I can spell points. To do this, you set f of x equal to 0 and solve. So we want to know, where is x squared minus x minus 6 equal to 0? It's a quadratic that fortunately factors as x minus 3 times x plus 2 equals to 0. Set each factor equal to 0 individually, and we get two values here, x equals to 3 and x equals to -2. These are what we refer to as our boundary points. We're going to go ahead and we're going to plot those on our axis here. Okay. Keeping in mind that if I look at the type of inequality we have, Notice that this is a strict inequality, it's strictly greater than, which means that these 0 points will not be able to be included in the solution set. So both of those are going to be represented as open circles. What we now need to do, if we look at the 2 points that we have, our 2 points subdivide the number line up into 1, 2, 3 different regions. And what we do now is we take a test point within each region, we're going to plug it into f of x to determine the sign of the function f of x within each of those regions. So for example, in region 1, I might use as a test point, let's say x equals to -3. Doesn't matter what value you pick, it just has to be in the defined region. And now you're going to plug it into the function. F of -3 is going to be -3 squared minus -3 minus 6, which is 9 plus 3 minus 6, which is 9 plus 3, which is 12 minus 6, which is 6. So in particular, that's greater than 0. So we know that in region 1, the function f is going to be positive. Let's take a look at region 2. A good test point to use in there perhaps would be x equals to 0. If I plug 0 into that function, we get 0 squared minus 0 minus 6, which is -6, which is less than 0. So in region 2, the function is negative. And if I pick a test point now in region 3, maybe something like x equals to 4, f of 4 is going to be 4 squared minus 4 minus 6. That's 16 minus 4 minus 6, which is going to be positive 6, which is greater than 0, or positive. And now to finish this up, we're ready to write out the solution set. To do this, you need to look at what is the direction of the inequality facing compared to your f of x. Notice that it says that it has to be greater than 0. So we're looking for the places where f of x is greater than 0, i.e. we want the intervals on which f is positive. That's going to be region 1, and it's also going to be region 3. So writing out our solution set is going to look like this. The solution set is everything from -infinity up to, but not including -2, and then union everything from 3 to positive infinity. Let's take a look at another one. Let's take a look at 34. So in question 34, it's similar type. It's another quadratic inequality. We have x squared plus 3x less than or equal to 0. Notice that thankfully the first step is already done for us. We have one side to be equal to 0. So we can define f of x to be x squared plus 3x. We're now going to use this to find the boundary points. You set f of x equal to 0. This is going to give us x squared plus 3x equals to 0. This factors as x times x plus 3 equals to 0. We have x equals to 0, x plus 3 equals to 0, and so we get x equals to -3 as well. So for this particular example, we have two boundary points. They are -3 and 0. And be very careful. It's really important that whenever you plot your boundary points on the real line, make sure you have them represented in the proper order, right? -3 is less than 0. So make sure you put -3 to the left, 0 to the right. Let's now consider whether or not these points can be included. Because it's less than or equal to, that equality will include these parts as a part of our solution set. So -3 is included and 0 is included. Those two numbers break up the number line into 1, 2, 3 distinct regions. And now we're going to use the method of test points to check the sign of f of x within each interval. So let's go ahead and do that. In region 1, perhaps we could use the test point x equals to -4. We plug it into the function like this. F of -4 is equal to -4 squared plus 3 times -4. That's going to be 16 minus 12, which is positive 4. So in region 1, f is positive. In region 2, I can use the test point -1, for instance. F of -1 is -1 squared plus 3 times -1, which is 1 minus 3, which is -2. So in region 2, it's negative. And then in region 3, let's use the test point x equals to positive 1. F of 1 is 1 squared plus 3 times 1, which will be 4, which is greater than 0, which is positive. So we've now filled out our sign chart, and it's time to write out our final solution. We need to look at the direction of the inequality. Here, this is set up so that it looks like f of x is less than or equal to 0. So we need the intervals on which f is negative. And that's going to be region 2. So our solution set to this inequality is going to be the interval -3 to 0 included. Let's go ahead and take a look at the next question. In question 35, we have the polynomial equation 2x cubed plus 3x squared minus 8x plus 3 equal to 0. And we're asked to solve this given that x equals to 1 is a 0. So one of the things that we know is that this is a polynomial equation of degree 3. Therefore, the fundamental theorem of algebra tells us that this equation should have 3 solutions in a set of complex numbers. The fact that we know that x equals to 1 is a solution means that we can perform polynomial division by the factor x minus 1 to break this thing down. To do that polynomial division, oftentimes it's easy to do synthetic division, so that's what I'm going to do. I'm going to synthetically divide this polynomial by 1. And if it's truly a 0, then that should leave no remainder. Let's check this. To do synthetic division, the first number comes straight down. You take the number on the bottom times the number in the block. 1 times 2 is 2. Add to go down. 3 plus 2 is 5. Bottom times block gives us 5. Add to go down, we get -3. Bottom times block gives us -3. Add to go down, and we get 0. So if you remember our factor 0 theorem, we have a remainder of 0, which does show that x equals to 1 is a root, which means that x minus 1 is a factor of this polynomial. The sequence of coefficients that we get, 2, 5, and -3, would correspond to the polynomial 2x squared plus 5x minus 3. Therefore, to find the rest of the zeros of this original function, it now resorts to finding the zeros of this polynomial portion. Okay. And to do that, luckily this factors. This will factor as 2x and x. This is going to be a 3 and a 1, a plus and a minus. So we factored it. We can now set each factor equal to 0 independently to get our other two zeros. Solving for this one will give us x equals to -3. Solving for this one will give us x equals to positive 1/2. One of the things with synthetic division we talked about, be very careful. In your dividend, you have to have every power of x from the highest power down to the constant displayed here. If you have a polynomial where the dividend is missing certain terms with x, you need to plug them in with a synthetic division with a bunch of zeros for their coefficients. So for example, if you wanted to divide, let's say, into x squared plus 1, this is really the same thing as x squared plus 0x plus 1. So it would look like 1, 0, 1 if you were to synthetic divide into that. Let's take a look at 36. Same style of question. we want to solve the equation x cubed plus 2x squared minus 5x minus 6 equals to 0. And now we're told that x equals to negative 3 is a 0 of this. So let's go ahead and break it down. We can do synthetic division. It's going to be 1, 2, negative 5, negative 6. First one comes down. Bottom times block. Add to go down. Bottom times block. Add to go down. Bottom times block. Add to go down. And of course we get a 0 here. So we divided it out. We already know that x equals to negative 3 is one of our solutions. The remaining solutions to this equation will come from the solutions to x squared minus x minus 2 equals to 0. Again, that's our quotient sequence. This one also factors as x minus 2 times x plus 1 equals to 0. Set each factor equal to 0 individually. We find our other two solutions are x equals to 2 and x equals to negative 1. Take a look at question number 27. We are asked to graph negative 2x plus 3 and label 2 points on the graph. So we have f of x equals negative 2x plus 3. And this is where it's good to recall. So this is an exponential function. It's good to recall the two classes of exponential function. So both of these have as an x-intercept the order pair 0, 1. These are the graph of b to the x. The first one is when b is bigger than 0. The second class is when b is between 0 and 1. The parent function, if we look at this graph of f of x, the parent function is going to be the graph of 2 to the x, which would be an exponential of the first type, so it should have a general shape that looks like this. The only other thing that we need to consider is how it's going to be transformed. Well, the plus 3 is a vertical shift up 3, and this negative, which is out in front, is going to be a reflection with respect to the x-axis. And I also should have mentioned it here, but for these exponential functions, remember they both have as a horizontal asymptote y equals to 0. So we would need to reflect this one first. So if you reflect this about the x-axis, it would look like this first. This would be the graph of negative 2 to the x. It would have this point, which would be 0, negative 1, and the asymptote would still be the same. If you were to now take all of those points and move them up 1, first of all, notice that the asymptote would move up 3 spots. So instead of the horizontal asymptote being at y equals to 0, the horizontal asymptote is now at y equals to 3. The order pair, which was at 0, -1, if you move that up 3 spots, that's now going to be at 0, 2. And because of the reflection, the shape of the graph looks like this. So this is the graph of negative 2 to the x plus 3. It once again was obtained from the graph of our parent function, 2 to the x, which is an exponential graph of type 1. And then we had a horizontal reflection about the x-axis, and a I guess that'd be a vertical reflection. It's a reflection about the x-axis, and then it was vertically shifted up 3 units. To summarize some of the key points that they want within the context of the question, they ask us for the y-intercept. That's this point here, which is 0, 2. You could have also found that simply by plugging 0 into the function. F of 0 is equal to negative 2 times to the 0 power plus 3. 2 to the 0 power is 1. So it becomes negative 1 plus 3, which is 2. The horizontal asymptote, we see that after the transformation, that now has equation y equals to 3. The domain of any exponential function we know is all real numbers. But if we look at the range, particularly from the graph, this graph goes all the way down towards negative infinity, and it goes up as high as 3, but it doesn't quite get there because of the asymptote nature. So its range goes up to 3, but the 3 is not included. In question 38, the next series of things that we have involve our logarithmic and exponential notation. So remember, whenever you're dealing with a logarithm, there's 3 key pieces. You have the base, I'm going to call it the value on the inside, and then you have the exponent on the right-hand side. I don't want to call it e, but let's call it k. This is equivalent to the following exponential statement. If you take the base, if you raise it to the exponent, this should be equal to the value on the inside. So this is the base. It's located as a subscript of the log. If it's not stated, if it's not listed, then it's understood to be common log, which is log base 10. If they use the ln notation, then we know implicitly that that's log base e. The exponent is on the other side of the equal sign. That's what the log is equal to. Logs are really exponents. And the thing on the inside of the logarithm is the value. So as long as you can keep track of those 3 pieces, it's fairly easy to convert back and forth between the log form and the exponential form of an expression. For example, in 38 part A, they want us to change m equals 6 squared into log form. So it's going to be log of the base is 6, the value is m, and the exponent is 2. So m equals 6 squared is equivalent to log base 6 of m equals to 2. For this next one, if it's the ln, that's log base e. So it's the exponent, it's the base e, to the exponent 7 equals the value. So the ln of x equals to 7 means that e to the 7th equals x. In question 39, we want to find the value of these logarithms. I'll do one of them, and I'm just going to kind of state the answers. But for example, with the first one, here's how you would work these out if you get stuck. If I want to find log base 2 of 1 over 8, if you don't know what that value is, call it a question mark. Or, I don't know, call it x. Take that log statement and then convert it back to an exponential statement. The base to the exponent equals the value. So to find the value of log base 2 of 1/8, it's equivalent to asking the question, 2 to what power equals 1 over 8? And an exponential equation like this, we said we can solve by, in this case, rewriting them both as the same base. 1 over 8, we know that 8 is 2 to the 3rd. Because of the reciprocal nature, that's a negative exponent. So 1/8 is the same thing as 2 to the negative 3rd power. And if the bases are equal and the values are equal, then that implies that the exponents have to be equal. So that's going to be negative 3. Okay. So log base 2 of 1/8 is equal to negative 3. Precisely because if you take 2 to the negative 1/3 power, that gives us a value equal to 1/8. So this is negative 3. You can do the same thing here. Log base 4 of 64 is asking the question, what exponent would you have to raise the base 4 to in order to get the value 64? That's going to be 3. Log base 9 of 3 is asking what exponent do you have to raise 9 to get 3? Well, 3 is the square root of 9, and we know that the square root is the 1/2 power. C and F are highlighting the inverse nature of log base b with the exponential function b to the x. Because these are inverses, you can think of the e and the ln as canceling, so this should be equal to 3x. And likewise, the function log base 4 and the exponential function 4 are inverses, so this equals to 10. And this is just a value, you can work it out. A square root is a 1/2 power, and a 1 over is a reciprocal, so that's a negative exponent. So log base 3 of 1 over the square root of 3, that should be equal to negative 1/2. In the next set of questions, we are asked to either condense or expand a logarithm. In order to do that, we need to lean on the three key properties of logs. Okay, the first one is what we call the product rule. The product rule for logs says that if you have, and I'm just going to write it with common log notation just to save some writing, but if you have log base any base of n plus log base m, this can be written as a single log of the product of the values, m times n. If you have log base n minus log base m, maybe I should put the m first. Makes more sense alphabetically. It's also how it was in the notes. This is m times n. Log base m minus log base n is log base m divided by n of a single log. And then the last rule we have is what's called the power rule. If you have a logarithm of some expression being raised to a power, that exponent can be brought out in front as a multiplication. This is equal to k times log m. So the first one is the product rule, the quotient rule, and then the power rule for logarithms. And again, anytime you have an equation, there's two sides to any equation. Going in this direction, we can use it to condense and write as a single log. Going in reverse is oftentimes helpful if you're asked to expand or write as multiple logs. Let's take a look at question 40, part A. In question 40, part A, we want to write as a single logarithm. We have 2 log base b of y minus 3 log base b of x. The first part for this would be to bring the exponents inside. Bring these coefficients inside as exponents using the power rule. This is equivalent to log base b of y squared minus log base b of x cubed. Now that we've cleared the coefficients off from out in front of the logs, we can now apply the quotient rule to say that this is going to be a single log. This is log base b of the first value, y squared, divided by the second value, x cubed. Okay. So starting with two logarithms, we are able to use properties of logs to condense them into a single log. Let's do the same thing with part B. Part B, we have 1/3 common log A plus 4 common log B. The first step, again, in condensing these is we need to bring those coefficients or factors, if you will, inside as exponents. This is going to be log of a to the 1/3 plus log of b to the 4th power. And now that we have the coefficients cleared out in front, we can use the product rule to say that this is going to be log of a to the 1/3 times b to the 4th on the inside. For those of you that like to it, if you don't want to write the 1/3 power, we know that that's the same thing that's equivalent to the cube root. So you could even write it as log cube root of a times b. Let's take a look at the next set in question 41. We're going in the reverse order. So starting with a single log, we're asked to expand it. First things first, we can use the quotient rule to say that this is the log of the numerator minus the log of the denominator. This first term is a product, so we can use the product rule to split that apart. This is log y squared plus log squared of x minus log of 100. We can next use the power rule to bring these exponents down in front. This is going to be 2 log of y plus, remember, the square root of x is the same thing as x to the 1/2 power. So this is going to be 1/2 log x minus, and now this is a value we can figure out very easily. Common log of 100, that's log base 10. So you're asking what exponent do you have to raise 10 to in order to get 100? And the answer is that's going to be an exponent of 2. So we've split it apart and expanded it as much as we could. We get 2 log y plus 1/2 log x minus 2. Let's do another one of these. We have log base 5 of 25 x squared. That's a product on the inside, so we can use the product rule. This is log base 5 of 25 plus log base 5 of x squared. This is yet another value we can calculate explicitly. Log base 5 of 25 is going to be equal to 2, simply because 5 to the second power gives us 25. And then for the second term, we can use the power rule to bring that 2 down in front as a multiplication to get log base 5 of x. So that's your answer to part B. We're able to successfully expand this logarithm. Let's go ahead and take a look at the next example. In question 42, we now shift our attention to exponential equations. We want to solve 4 raised to the 2x minus 1 equals 2 to 64. This kind of exponential equation is one where we can solve it by rewriting both sides as a power of the same base. The left-hand side is already base 4, and one of the things that we know is that 64 is 4 to the third. If the bases are equal and the values are equal, then because of the one-to-one nature of the exponential function, then this implies that the two exponents have to be equal. So we can set 2x minus 1 equal to 3 and solve for x. Add 1, add 1. We get 2x equals to 4. Divide both sides by 2, and we get as a solution x equals to 2. In question 43, we run into kind of the other type of exponential equation where it's not going to be possible to rewrite both sides of the same base. The first step on a question like this, however, is we need to isolate and get the exponential term all by itself. So I'm going to subtract 5 from both sides so that we can rewrite this as e to the x equals 5. From here, to get the x solved for, remember, e and 5, you can't write those as the same base. So the technique this time would be to take a logarithm of both sides. And for us, we always want to take one of the logarithms that's presented in the calculator. It doesn't matter which one you use. You can either use common log or natural log. I prefer to use natural log. So I'm going to take the natural log of both sides. And then notice on the left-hand side, because of the inverse nature of the ln of e, those two things cancel directly, and we get that the x is equal to the ln of 5. Usually in a question like this, we're also asked to give an approximate solution. So this is the exact answer. And if you wanted to round this to 2 places, we could also give an approximate answer of 1.61. This would be approximate. Let's do another one of these. Question 44, we have 5 raised to the x minus 2 equals to 16. We already have the exponential term by itself on the left-hand side. It's not possible to write both 5 and 16 as the same base. So let's go ahead and start by taking the natural log of both sides. This will allow us on the left-hand side, because of properties of logs, we can use the power rule to bring that x minus 2 out in front so that we have x minus 2 times the ln of 5 equals to the ln of 16. The next step to kind of write this thing nice and neat is let's get rid of the ln of 5 by dividing both sides by ln 5 so that we get x minus 2 equals the natural log of 16 divided by the natural log of 5. And then lastly, to get x by itself, we could add 2 to both sides, and we would come up with the exact solution, x equals the natural log of 16 divided by the natural log of 5 plus 2. So there's our exact solution. We also, on problems of this type, like to give an approximate solution. To 2 decimal places again, this would be approximately equal to 3.72. And that's our approximate. On the exam, you absolutely have to make sure you put the exact answer, and I will also request the approximate given to 2 decimal places, just like we're doing here in the review. The last set of questions that are going to be on the test are our logarithmic equations. Let's take a look at 45. We have the ln of x plus the ln of x minus 5 is equal to the ln of 6. This is an example of a logarithmic equation where we have logs on both sides of the equation. In order to solve this, what we want to do is condense both sides so that we have a single log on each side. We can do that by, on the left-hand side, using the product rule to condense these logs. If we have the sum of the logs, we know from the product rule that's the log of the product, meaning this is the same thing as the log of x squared minus 5x equals the ln of 6. Now from here, much like the exponential function, the logarithmic function is also one-to-one. So if you have 2 logs on either side of the equation that have equal values, so if you have the log of the same base and the values are equal, then that means that the inside parts also have to be equal as well. So this implies that x squared minus 5x has to be equal to 6. This is a quadratic equation. We know how to solve it. Get one side to be 0 by subtracting 6 from both sides. You can now factor this. This factors as x minus 6 times x plus 1 equals to 0. Set each factor equal to 0 individually, like this, and we get x equals to 6, x equals 2 to negative 1. With your exponential equations, please make sure, with your logarithmic equations, please make sure you check your solutions. X equals to 6 will check out. If you plug it into the original, it will give you a true statement. However, if you plug x equals to negative 1 in, right off the bat, this is the ln of negative 1 plus the ln of negative 1 minus 6 equals the ln of 6. That produces a negative inside of a natural log, which we know is undefined. So you don't necessarily have to check everything all the way through, as we discussed in the lecture, provided that value of x doesn't give you a 0 or a negative inside the log, it will be a solution, okay? So we get one solution to this one, and that is x equals to 6. That other one was an extraneous solution. We cannot have negatives inside of a log. Let's take a look at the next one. In 46, we have log, common log, of 3x minus 3 minus the log of 4 equals log of x plus 1. This is very similar to the last example where we have logs on both sides of the equation. So we want to condense both sides so that we have just a single logarithm. On the left-hand side, we can do this by using the quotient rule for logs. If we have the difference of the two logs, we can write that as the log of the quotient. From here, because log is 1 to 1, if we have log base 10 on both sides and the values are equal, then that implies that the inside values have to be equal. So we're able to go ahead and set 3x minus 3 over 4 equal to x plus 1. We can solve this equation by eliminating the fractions first of all. Let's multiply both sides by 4. We would get 3x minus 3 equals 4x plus 4. We now need to get all of our x's to one side. So I'm going to subtract 3x from both sides. We get to negative 3 equals x plus 4. And now subtract 4 from both sides, and we get negative 7 equals 2 to x. Again, you should want to check this. If you plug negative 7 in, I can see that very quickly that's going to make some of our log terms a negative. So that means that this value, x equals to negative 7, is going to be extraneous. It was the only value of x we came up with. However, it's not a solution to the equation, which means the answer to this equation would be no solution. So this one has no solution. Let's take a look at 47. In 47, we have log base 2 of x plus 2 plus log base 2 of x minus 1 equals to 2. For this particular equation, it's a log equation where we only have logarithms on the left-hand side. The strategy for solving these is we want to condense that left-hand side into a single log. This can be done using the product rule, like this. So this is equal to log base 2 if you expand it out. Simplifying, I'm not going to show that work, but it's going to be x squared plus x minus 2 would be equal to 2. And then the key to solving these is once you have the left-hand side condensed into a single log and the right-hand side is equal to a number, now what you want to do is convert to exponential notation. So we have the value, which is the thing on the inside. The x squared plus x minus 2 should be equal to the base raised to the exponent. So this should be equal to 2 squared. This is a quadratic equation now. We can solve it. Get one side to 0. We have x squared plus x minus 6 equals to 0, which factors as x plus 3 times x minus 2 equals to 0. Set each factor equal to 0 individually, and we get two proposed solutions. Those proposed solutions are x equals to negative 3 and x equals to 2. And again, with log equations, be sure you're checking these. Okay, if I check negative 3, not even going all the way through, but I see that plugging negative 3 in will give me some logs with a negative value on the inside. So that one's going to be extraneous. It doesn't work. If I plug 2 in, I'm not going to have any issues with negative logs, and so that one would check out if you work it all the way through. We get just one solution, x equals to 2. All right, we have one left. So the last question on the review, this is 48. We want to solve log base 4 of x plus 2 minus log base 4 of x minus 1 equals to 1. This problem is going to be solved the same way. We have logs on just one side and a number on the other. So we're going to use properties of logs to condense the left-hand side. That's going to be the quotient rule. We get log base 4 of x plus 2 divided by x minus 1 equals to 1. The next step is now to convert it to a exponential statement. The value on the inside is equal to the base raised to the exponent power. That's going to be equal to 4 to the first, i.e. x plus 2 over x minus 1 equals to 4. This is a rational equation. Solve it by clearing the fractions, multiplying both sides by x minus 1. Cancel, cancel. We get x plus 2 equals, distribute, 4x minus 4. Get all of your x's to one side, so subtract x. We get 2 equals 3x minus 4. Isolate the x, add 4. We get 6 equals to 3x. Divide 3. Cancels, and we should get x is 6 divided by 3, which is 2. Again, before I box this, I should have said to check it. Plug that back in. Make sure you get a true statement. This one I'll actually show. Let's just show this together really quickly. If you have log base 4 of 2 plus 2 minus log base 4 of 2 minus 1, does that equal to 1? Well, that's going to be log base 4 of 4 minus log base 4 of 1. Log base 4 of 4, from properties of logs, we know that that's 1, minus, we know that log base b of 1 is always equal to 0. And so sure enough, it does check out and it does give us the value 1. And we would have known that ahead of time, because if you just do a quick glance, substituting x equals to 2 into this would not produce a negative value inside of your logarithm. So I hope this helps everybody. That's the end of the final exam review. Good luck everybody on your test next week.